Okay, so chapter 5 is going to be talking about using a new technique for solving differential equations, but before we actually get to that technique, we need to do a little bit of review. So in this first part, we're just going to talk about what a series is, what a power series is, maybe what a Taylor series is, talk about a little bit of algebra. So just to start things off, remember how we learn these things in Calc 2? So initially we just talked about a sequence, and a sequence is just a listing of terms. Then we talked about a series, and then we talked about a power series, and then we talked about the Taylor series, right? And so we're going to go through each one of these just really briefly, talk about some of the important features. Some things we'll spend more time on than others. But sequence and infinite series, I guess, is another way to say that. Power series, Taylor series. Okay, so a sequence is a certain listing of terms we just talked about. The order is important here. There's a time ordering of your values, right? And the typical question for a sequence is, what is the long-term behavior, which you can compute by taking the limit? Good. And so one way of taking the limit is L'Hopital's rule. We won't go too deep into that right now, but just to remind you what L'Hopital's rule is, if you have a fraction f of x over g of x, and that fraction turns out to be 0 over 0 or plus or minus infinity over plus or minus infinity, these terms, or these fractions here, are called indeterminate forms, in that they don't tell you anything about the limit, right? The limit may or may not exist. We have to do more work in order to see. Okay, and so in L'Hopital's rule, if you get one of these two forms, then you can take the limit by taking the limit of the derivatives. And some people forget this next part. That only works, by the way, provided that that limit exists. Okay, so we're going to do these later, but I just wanted to give you a little bit of reminder. Good, so let's move on to a series. So in a series, the main question is, what does it mean to sum an infinite number of things together? Right? So we answer that question by taking a look at the infinite sum here. And the infinite sum is defined to be the limit as n goes to infinity of the partial sums, right? So this term now is not an infinite sum. We're just summing the first n plus 1, capital N plus 1 terms, right? Going from 0 to n. Good. And so now we're seeing if the partial sums converge, and if they do, then we say that the limit exists and that the sum converges to a certain value. Partial sums converge, right? So absolute convergence is another type of convergence. That's when the absolute value of your terms, you take the absolute value of your terms and you sum, right? And that converges. So we might just note that absolute convergence implies convergence, right? So in fact, absolute convergence is a very strong type of convergence we're going to talk about in just a second. Conditional convergence is the type of convergence where the sum converges but not absolutely. Okay, so there's some kind of template examples of this we'll talk about in just a second. That we have tests for convergence, lots of tests. The integral test, comparison test. Actually, there's a limit comparison test as well. Alternating series test. The ratio test and the root test are the most popular that we learn in Calc 2. We're going to focus on almost exclusively the ratio test, and so we'll talk about that in just a second. I just wanted to mention, in common English, the words sequence and series are actually synonymous. Right? They mean that there are a bunch of things happening, but they happen in some order, like a series of events or a sequence of events. And so in colloquial English, because they are synonymous, it's easy to mix them up in mathematical terms too. But in mathematical terms, they're very different things, right? So a sequence is just a listing of things in order. There's an order. And a series is a sum. Okay, so they're very different things in English, so be sure and keep those two words straight. That's important. Okay, so enough of the lecturing. Let's go on. Ratio test for absolute convergence of a series. Good. The ratio test takes the limit of the n plus first term divided by the nth term. By the way, this is the sum that we're summing here, the sum that we're looking at. And so you take the limit as n goes to infinity of the ratio of the n plus 1 term to the nth term and see what that limit is. And if that limit is less than 1, then we say that the series converges absolutely. Now, some people stop there, but there is more to the ratio test than this. If the limit is bigger than 1, there's also a conclusion, and that is that the series diverges. And then the third part of that is if the limit is equal to 1, and if the limit is equal to 1, then there's no conclusion that can be made. Now you might be wondering why this is true, why this is less than 1, greater than 1, and 1. And the reason is because we're actually comparing this series to a geometric series. And if you've forgotten what a geometric series is, we're going to talk about it in just a second. But I just wanted to mention that the conclusions here you can remember as being the conclusions of the ratio or the geometric series, right? As your terms, except this is the comparison of the terms and not the terms themselves. So if the comparison is less than 1, by the way, if this was a geometric series, the n plus first term divided by the nth term would be r. So that's where you're kind of getting the r, right? And so this first one is that r is less than 1, so we have convergence. R bigger than 1, divergence, and if r is equal to 1, no conclusion. So that's one way to remember what the conclusion of the ratio test is. Good. So we're going to use that later on, but there's some other things that we wanted to talk about first. And here are just some template series to know. I've decided to put them all up at once here so you can visualize them. So this first series is the sum n equals 1 to infinity of 1 over n. And that is called the harmonic series. It comes up a lot. That's why we have a special name for it. And so we learn in Calc 2 that this series actually diverges. And the importance of this series really as a template series is this is kind of our first example where the terms of the series, the 1 over n, goes to 0, but the sum itself diverges, right? So that means that in order for a series to converge, not only do these terms need to go to 0, but they need to go to 0 fast enough. Okay, so that's kind of a good thing to remember. Good. So the next one, if you put a minus 1 to the n on the top, then we get something that's called an alternating harmonic series, and that is something that does converge. And so if you compare the alternating harmonic series with the harmonic series, right, you can see that the alternating harmonic series converges, but not absolutely, right? Because if you take the absolute value of the terms in the alternating harmonic series, you get the harmonic series, and we know that that diverges. Therefore, the alternating harmonic series is kind of our template example of conditional convergence. Good. And then a series that just comes up a lot because we compare it to everything is the geometric series. And just notice here that I'm starting my series at n equals k instead of 0, going out to infinity. Okay, in that case, then the sum of the geometric series, if r is less than 1, by the way, is ar to the k. That's the first term of your series, right? First term of the series divided by 1 minus the ratio, 1 minus r. Good. So that is the geometric series, and it converges absolutely. We prove that it converges absolutely if r is greater than 1. And actually, we also prove that it diverges if r is bigger than 1, and it's well, we don't need to say it's inconclusive at r equals 1, right? Because what happens, you can kind of see what happens here. If r is equal to 1, then you're just summing a an infinite number of times, and so that's going to diverge. Good. Okay. The last template series we want to remember is the P series. And so the P series is 1 over n to the P for some fixed P, right? So you can see here that you get the harmonic series if n is equal to 1, or if P is equal to 1, sorry. Right? And then something like 1 over n squared, that would converge absolutely because that P is bigger than 1. But if you had something like 1 over the square root of n, that converges slower than 1 over n, right? And so therefore it diverges. So this converges absolutely for P greater than 1 and diverges if P is between 0 and 1. Good. And the reason I'm writing up this P series is that if you tried to use the ratio test on a P series, the ratio test would fail. It would be inconclusive. And so it's always good to know what the conclusion is for the P series, so you don't have to use a ratio test for that. Okay, so those are the 4 series it's really good to know. Remember the names from Calc 2. Good. All right. So a power series then. We're moving from a series to a power series. The difference is a power series is a polynomial. So it actually depends on x. Now you'll notice that power series has a couple of things going on here. One is the base point, which is x sub 0, right? So your power series always has to be based somewhere, and that somewhere is the x sub 0. We're going to talk about the importance of that in just a second. But then you might have coefficients in front of your polynomial terms, in terms of your monomial, in front of your monomials that depend on n. Okay, so so convergence in this case will depend on x, right? So depending on x, you're going to get different series. In particular, if you put in x0, what happens? All the terms are 0 except for one term, a0. Yeah, a0 is going to be the only term left. Okay. Yeah, so it's always convergent for x equals x0. So the question then is the sum convergent for any other x? And that's where the ratio test comes in. So let's go ahead and take the limit of the n plus first term divided by the nth term of the series and see what we get. So please, please, please don't forget your absolute value bars. I see this a lot. Students drop these absolute value bars and their solutions get funky. Remember that we're testing for absolute convergence, so you need those absolute value bars. Good. Okay, so once you have these absolute value bars, you can bring the absolute values in here. And so write the absolute value of a product is the product of the absolute values. And so you can simplify this quite a bit here. And so we can bring in the a sub n plus 1 over a sub n, and then the absolute value of x minus x naught to the n plus 1 divided by the absolute value of x minus x sub naught to the n is just going to give you x minus x naught. Good, so you're always going to have this kind of a limit when you're dealing with a power series, right? So you might notice that the x minus x naught does not depend on n. So really the only thing you're looking at is this thing in front. You're looking to see if this thing has a limit. And so let's call that limit L, just for fun. And so by the ratio test then, if we get L times x minus x naught, then we need that to be less than 1 for convergence, right? Absolute convergence. Okay, so therefore, if x minus x naught is less than this 1 over L, then we get absolute convergence of the power series, right? Let's say that again. If x minus x naught is less than 1 over L, in this case, we get absolute convergence of the power series. And so this is a really important number. It's important enough that we give it a name, rho. Actually, that's not the name. This is rho, but rho is called the interval of convergence, or the radius of convergence, sorry. Rho is the radius of convergence. Okay, and so if x minus x naught is less than rho, we get absolute convergence. If, on the other hand, x minus x naught is bigger than rho, then the series will diverge, right, for the power series. And then if it's equal to rho, the test is inconclusive, right? And so therefore those points, by the way, there's going to be 2 points for this, right? X equals x naught plus rho and x equals x naught minus rho. Those 2 points have to be tested separately. Those are the endpoints of your interval of convergence. Good. So rho is an important number called the radius of convergence. All right, we're going to do some examples of finding the radius of convergence in just a second, but I just wanted to talk about some of the implications of having a radius of convergence. And that is, there's only really 3 types of convergence. I don't know how that happened here. For a power series. You may only converge at a single point, and if that's true, then it has to be the x equals x0. You might converge, the series might converge for every point, in which case we would say that the radius of convergence is infinity. Otherwise, we get the case that we were just talking about, right? We get some non-zero rho that's finite, and so we would say that this converges absolutely if it's less than rho, diverges if bigger than rho, and then you have to test the 2 endpoints separately. Okay, but the main thing here is that these are the only 3 possible outcomes when we talk about convergence of a power series, right? A single point, every point, or a nice symmetric interval based at x naught, right, with a radius of rho on either side. Good. All right. So there are some implications of this. Let's try an example. Suppose that this power series, a sub n x minus 3 to the n, converges for x equals 6. Then where else must the series converge? Go ahead and pause if you want to think about that for a second. Otherwise, let's take a graph. Here's a number line. I know that my base point is at x equals 3. Right, so my interval is going to be symmetric around x equals 3, interval of convergence, I should say. And so I also know that the series converges at 6. Therefore, I must converge, or the series must converge on a symmetric interval about 3. And so if this is 3 units up, it must also converge 3 units down. The only question would be, sorry about that, is what happens at the endpoint. So even though we converge at 6, we may not converge at 0. We may or may not. We don't know. We would have to have more information. So the most that I can say at this point is that the interval of convergence is at least open interval from 0 to closed interval at 6. Okay, so open at 0, closed at 6. It could possibly include x equals 0, but yeah, we would need more information. Good. All right. Let's go ahead and try some radius of convergence computations. So find rho if sigma is equal to, or if we have this sum. Go ahead and pause the video for a second if you want to give this a try yourself. So we're using the ratio test. Are you ready? Okay, so when we take the absolute value of these terms, notice that the minus 1 to the n is going to be irrelevant. It's going to become plus. And so we're just going to have the n squared times x plus 2 to the n over 3 to the n. Also, you might notice that 3 to the n will also, well, actually n squared and 3 to the n will always be positive as well. But I guess we won't do everything at once. Let's go ahead and take our limit. So here's the n plus first term. Now I'm going to divide by the nth term, and if I divide by a fraction, that's the same as inverting and multiplying, right? So I'm going to invert and multiply, so instead of taking the fraction. And now what I like to do is I like to combine these terms when I'm making my simplification. So notice that the 3's are here, so I'll group the 3's together, and then I'll group the n's together, and then I'll group the x's together. Okay, and so now it's a lot easier to simplify, right? Because 3 to the n over 3 to the n plus 1 is just 1/3. N plus 1 squared over n squared, that's going to stay there. I'm going to take the limit of that. And then x plus 2 to the n plus 1 over x plus 2 to the n. Notice that the absolute value bars, by the way, came in. Okay, that simplifies to just x plus 2. And so now when I take the limit, it's going to be 1/3, which we were talking about. The limit as n goes to infinity of this middle term, is 1. You could use L'Hopital's rule if you had to, otherwise you could just divide top and bottom by n squared, either way. Okay, and then that's times x plus 2. And so what does the conclusion of the ratio test need to be? We need our limit to be less than 1 in order for this to converge absolutely, which means that the absolute value of x plus 2 must be less than 3, and that gives us the radius of convergence. Yay! So again, take the n plus first term divided by the nth term, and it's easier if you just multiply by the reciprocal, right? Instead of dividing first. You can divide first if you want, but at some point you'll have to get to this stage. Good, and then group the terms to make it easier to simplify. And then when you take your limit, most of the limits we're going to be doing are pretty straightforward. So it's usually some kind of polynomial divided by a polynomial. All right, let's try another one. Find the radius of convergence if we have this sum. So this one looks pretty straightforward. We have a factorial going on here. I wonder where that's coming from. Okay, so if you're still with me, you haven't paused yet, so let's go ahead and give this a try. And so the ratio test again, we're going to take the n plus first term. I'm going to multiply by the reciprocal of the nth term, right? And so that's dividing a sub n plus 1 divided by a sub n. Good, and now I'm going to simplify by getting the pieces together, right? So n factorial over n plus 1 factorial, and then I'm going to bring my x's together. Good, and now when I simplify, remember that n factorial is the product of the integers from 1 to n, and n plus 1 factorial is the product of the integers from 1 to n plus 1. And so you can cancel the first n of those, and so you're going to be just left with 1 over n plus 1 here, right? And so let's simplify algebraically. The x's also cancel. By the way, please be careful when you're putting in the n plus 1 here. Put it in parentheses so you remember to distribute the 2 through. Okay, so that's why we get the x squared there. Good. When I take the limit as n goes to infinity, this x squared doesn't depend on n at all. And so that this whole thing depends on just 1 over n plus 1. And so what is this limit as n goes to infinity? That is 0. That's interesting because the limit is always 0. It doesn't depend on x. So what does that mean? That means the series converges for all x, right? The series converges for all x. Therefore, the radius of convergence is infinity. Good. Okay, I'm running a little bit short of time, but I wanted to do a couple more quick examples. We'll go through fairly quickly, so if you want to, you might want to slow the video down here or rewatch it from this point. So find the interval of convergence for this one. We're going to do exactly the same thing, except now we're going to be asking for what happens at the endpoints. Okay, so if you're finding the interval of convergence, you want to check the endpoints. So if you just do the ratio test, there's the n plus first term divided by the nth term. I guess I've already simplified it for you. And so when I take the limit, do you see what we're going to get? The n over n plus 1 will go to 1. 2 to the n over 2 to the n plus 1 will go to 1/2. And so this is just going to go to x plus 1 over 2. So I need that to be less than 1 in order for this to converge absolutely. Therefore, my radius of convergence is 2. And so what are the two endpoints that I have to check? Well, if I take x plus 1 equals 2, that means that x plus 1 is equal to either positive 2 or x plus 1 is equal to minus 2. So if I solve each of these equations, right, if I take x plus 1 equals 2, then x must be 1. And here x must be negative 3. So we have negative 3 and 1. So now we have to check our endpoints. And so if I plug in x equals minus 3, I get the following sum. And so here you can see what's going to happen. We get a minus 2 to the n over 2 to the n. And so I'm going to expand this by taking this to be minus 1 to the n times 2 to the n, and then the 2 to the n's will cancel, leaving me with just minus 1 to the n divided by n. And does that series look familiar? It is the alternating harmonic series which converges, but only conditionally. Very good. And so x equals minus 3 can be included in our set of x for which the series converges. Good. How about the next one? If x equals 2, then I get 2 to the n over 2 to the n times n, and those, 1 over n, that's going to diverge, right? So I would not include the point x equals 1. And so the interval of convergence includes the point -3 and deletes the point x equals 1. Very good. Now, I just wanted to mention just really briefly here what happens when you don't have just an x here. So let's just go ahead and run through this. This is a pretty brief example here. So in the ratio test, we put together our usual fraction, and you get something like this. So the limit just turns out to be 1. And now the question is, what do you do with this? This needs to be less than 1. Be sure you factor out the 3, right? So that the radius of convergence is 1/3 and not 1, right? So you need to have the form x minus a here. This needs to, or x minus x sub 0 here. This must have the form x minus x sub 0 here. Good. So that's how you get the radius of convergence. Good. I think we finally made it. I wonder how much time I've gone over. Next, we're going to take a quick review of the Taylor series. See you then.